In this lesson, we will learn about series RLC resonance. Okay, as we have seen previously, if a RLC circuit consists of in series we have R, L, and C, then the total impedance we can just sum all these three impedances in which we'll get this equation. Okay, so, we have also seen if this is bigger than this, okay, this component, the inductive component is bigger than the capacitive component, then the whole circuit will be inductive. On the other hand, if the capacitive component, this one, the capacitive impedance, is larger than the inductive impedance, then the entire circuit will become more capacitive. Okay, what if these two values are the same? If these two values are the same, this and this are the same, then this one will become 0 and the circuit will only have the resistive component. This is what we call resonance. Okay, resonance, where the impedance has only the real part. Okay, so a circuit is said to be resonance if the inductive and capacitive reactance are equal. This is equal to this, and we can see here if the capacitive reactance is bigger, then the circuit is more capacitive this side. Okay, if the inductive reactance is bigger, then the circuit becomes more inductive. But if both are equal, then it is called resonance. Okay, as we change the frequency, okay, this curve, when the frequency is changing, we can see here, so frequency is related to your omega. Okay, just 2 pi f is equals to omega. When your frequency is increasing, when the omega is increasing, this one will become bigger and bigger. That's why at large omega, it becomes the j omega L will become large. So this becomes inductive. The omega L becomes large. At small omega, you see this component, when omega is smaller, this whole thing becomes bigger because it's at the denominator. So at low frequency, your 1 over omega c becomes large. So here it's capacitive, here it is inductive. Okay, so this is capacitive, this is inductive. When your omega at a certain value such that your this and this are the same, the omega L is equals to your 1 over omega c. Okay, when your frequency is such that these two are the same, then we call it resonance. Okay, it is neither inductive nor capacitive. So what is the value where this is equals to this? We can just solve this equation. Your omega L equals to 1 over omega c, and then you bring the omega here, you get omega square is 1 over LC. Okay, I bring the omega here, I bring the L down. Then omega is 2 pi f. So 2 pi f square equals to 1 over LC. From here, we can get the equation for f. Okay, yeah, f square is 1 over, you bring the 2 pi down to, okay, you can use some algebraic manipulation and finally you'll get this equation. Okay, the 2 pi LC, there's a square here, and then you square root, this one will go away, you'll have a square here. That's the equation given here. Okay, so I erase this. This is the equation for your resonant frequency. So if in the question you are given your L and C and asked to find what is the resonance frequency, just substitute here. Okay, substitute here. And by rearranging this equation, we can also get these two equations. In case your resonance frequency is given and capacitance is given, you can find the inductance at resonance. Or if your frequency is given, inductance is given, you can also find the capacitance at resonance. Okay, finally, series resonance circuits can be found in many different applications, okay, such as filters in AC, noise filter, radio, television tuning, and so on, okay, for different frequencies. Yeah, that's all. Thank you.